Imagine a universe with no speed limits, a cosmos where objects accelerate endlessly, racing faster and faster without bound. It's a seductive idea, one that captures imagination and has fueled centuries of speculation, from mythic chariots to futuristic spaceships. Yet, the universe has a rule so fundamental, so unwavering, that it shapes everything from the tiniest particle to the largest galaxy. Nothing with mass can reach the speed of light. This is not a suggestion, a guideline, or a convenient approximation. It is a hard limit, encoded in the very fabric of space-time, and it is a reason why our dreams of infinite speed remain forever out of reach. The story begins with Einstein's theory of special relativity, a framework that revolutionized our understanding of space, time, and motion. Before Einstein, it seemed natural to assume that speeds could simply add up. If a train moves at 50 kilometers per hour and a passenger walks forward at 5 kilometers per hour, their speed relative to ground is 55 kilometers per hour. In a classical world, it might seem that there is no ultimate cap. We could just keep adding velocities to go faster. But Einstein revealed that the universe is not classical and that space and time are intertwined in a way that prevents anything from exceeding a particular speed. The speed of light in a vacuum, approximately 299,792 kilometers per second. At first, the speed limit seems arbitrary, almost poetic. Why light? Why this particular number? The answer lies in the structure of space-time itself. Light does not simply travel fast. It occupies a special position in the geometry of the universe. The laws of physics are the same for all observers, regardless of their motion, and light acts as a cosmic benchmark that connects space and time. Attempting to accelerate a massive object toward this limit reveals a surprising truth. The closer you get to light speed, the harder it becomes to go faster. Energy requirements grow without bound, stretching toward infinity. To reach light speed, an object with mass will require infinite energy, a demand the universe will never meet. This is where the concept of relativistic mass comes into play. As an object accelerates, its effective mass increases, not because the atoms themselves become heavier, but because their inertia, the resistance to acceleration, grows. The faster you try to go, the more energy it takes to accelerate each kilogram of matter. At low speeds, this increase is negligible. You barely notice it when driving a car or riding a bicycle. But as you approach light speed, it skyrockets. A spacecraft accelerating toward this limit would demand energy beyond comprehension, consuming entire stars' worth of fuel for a fraction of the journey. The universe imposes its rule not through arbitrary decree, but through the interplay of mass, energy, and the geometry of space-time. Even time behaves differently at extreme speeds. According to special relativity, time slows down for an object as it approaches light speed, a phenomenon known as time dilation. A traveler in a near-light speed spacecraft would experience minutes, while years pass for those left behind. This effect is real, measurable, and has been confirmed through experiments with atomic clocks on fast-moving planes and satellites. Time itself conspires against any attempt to reach the cosmic speed limit, stretching the journey and bending reality around the traveler. It is not just that reaching light speed is impossible. The very rules of the universe prevent it from being meaningful in a classical sense. This cosmic speed limit has profound implications for exploration and imagination. The stars are unimaginably far apart, and the distances grow effectively insurmountable when constrained by light speed. Even a journey to the nearest star system, Alpha Centauri, which lies 4 light-years away, would take 4 years traveling at light speed, and longer than a human lifetime if you remain within the limits of feasible acceleration. The universe is immense, but relativity ensures that it remains forever distant, enforcing boundaries that shape the very nature of cosmic travel. Yet physicists have not abandoned the dream of reaching beyond these limits. Ideas like warp drives, wormholes, and hyperspace corridors emerge on the margins of theoretical physics. These concepts do not violate relativity directly. Instead, they exploit its flexibility. A warp drive, for example, would compress space in front of the spacecraft and expand it behind, allowing the ship to traverse distances faster than light would in normal space, without locally exceeding the speed of light itself. Wormholes, hypothetical tunnels through space-time, could connect distant points instantaneously. While these ideas are mathematically intriguing, They remain speculative, demanding exotic forms of energy and technology that are currently beyond reach. They are reminders that the universe's rules are rigid yet complex, and that any shortcut through space-time requires conditions the cosmos may never provide. Even at the scale of particles, light-speed barriers dominate the behavior of matter and energy. Electrons and accelerators can be pushed to astonishing fractions of the speed of light, but each incremental gain requires exponentially more energy. Protons in a Large Hadron Collider reach 99.9999991% of light speed, consuming immense resources, yet they can never reach the absolute limit. Nature's speed cap is absolute, unavoidable, and elegantly embedded in the laws of physics. It is a cosmic safeguard that ensures the universe remains coherent, causality preserved, and energy conserved. This limit also shapes the universe on a grand scale. Light from distant galaxies takes billions of years to reach us, and the observable universe is constrained by this finite speed. Nothing we send can outrun light to reach the most distant corners, and information cannot travel faster than this ultimate cosmic velocity. The speed of light is not merely a technical limitation. It is a lens through which we perceive reality, the frame that structures the flow of cause and effect, the rhythm that underlies everything from the tick of an atomic clock to the spiral of galaxies. And yet, the impossibility of reaching light speed does not mean stagnation. Relativity introduces astonishing phenomena like length contraction, where objects appear shorter along the direction of motion at high speeds, and relativistic momentum, where collisions at near light speeds behave in counterintuitive ways. The universe is not merely a set of barriers. It is a playground of consequences, revealing new realities as we approach its ultimate limits. Even though light speed is unreachable, it defines a frontier, inspiring innovation, exploration, and imagination. In the end, the cosmic speed limit is more than a technical obstacle. It is a profound statement about the nature of reality. It ties together energy, mass, time, and space, forming a web of constraints that preserve the structure of the universe. It reminds us that the cosmos is governed by immutable laws, yet also challenges us to think creatively, to explore theoretical loopholes, and to imagine possibilities that transcend classical intuition. Reaching light speed may be forever impossible, but the pursuit of understanding illuminates the very foundations of physics. The story of why we can never reach light speed is not just about limits. It is about insight. It reveals the subtle, interwoven principles that govern the cosmos, the extraordinary consequences of relativistic physics, and the delicate balance between possibility and impossibility. In understanding why the ultimate speed is unattainable, we glimpse the profound beauty and coherence of the universe, a realm where constraints are not mere obstacles, but the very structure that makes existence intelligible. As we dive deeper into the consequences of the cosmic speed limit, the picture becomes even more fascinating and more daunting. The laws of relativity are not just abstract mathematics. They govern every attempt to accelerate matter toward the speed of light. One of the most striking consequences is the way energy and mass behave at extreme speeds. In our everyday world, pushing an object requires a predictable amount of force. A car accelerates in proportion to the energy we supply. But as speeds approach light's ultimate limit, this relationship changes dramatically. The faster an object moves, the more the effective mass increases, a phenomenon often referred to as relativistic mass. Imagine a spacecraft hurtling through space. At moderate speeds, Newtonian mechanics gives us an accurate picture. Push a thruster and the ship accelerates. But as the ship nears light speed, each additional increment of velocity demands exponentially more energy. To move from 0.9 c to 0.99 c, a seemingly small step, the energy required is far greater than that needed to accelerate from rest to 0.9 c. Push towards 0.999 c, and the energy needed becomes astronomical. To reach light speed itself, the energy requirement becomes infinite. The universe imposes this rule with perfect consistency. No finite amount of fuel, no technological breakthrough can propel a massive object to light speed. It is an absolute barrier. Time, too, bends under these extreme conditions. Time dilation, another prediction of relativity, means that as an object accelerates, time for that object slows relative to a stationary observer. If an astronaut could approach near light speed, Hours for them could correspond to years for someone on Earth. This effect has been verified repeatedly through experiments using high-speed particles and precise atomic clocks. Time itself becomes a fluid, stretching and contracting depending on the relative velocity. In practical terms, this makes near-light speed travel not only energy prohibitive but also temporally disorienting. Even if we could somehow supply the required energy, the journey would unfold differently for those aboard than for those left behind, creating profound complications for any attempt at interstellar exploration. Length contraction adds another layer of strangeness. According to relativity, as an object approaches light speed, it appears compressed in the direction of motion to an outside observer. The faster you move, the shorter your measured length becomes, until at light speed, classical intuition breaks down entirely. Space itself seems to distort, an effect deeply counterintuitive but mathematically consistent. These distortions are not theoretical curiosities. They are real consequences of the universe's structure, consequences that any traveler approaching extreme velocities would experience, making relativistic motion an arena of paradoxes and wonder. Momentum, too, behaves differently near light speed. In classical mechanics, momentum is simply mass times velocity. But as velocity approaches c, momentum grows faster than velocity, reflecting the relativistic increase in effective mass. Collisions at these velocities do not follow the rules we know from billiard balls or cars. The kinetic energy involved is staggering, and interactions can produce entirely new particles. The universe becomes a laboratory of extremes, revealing phenomena that seem alien to our everyday intuition, yet are the natural consequences of relativistic laws. This interplay of energy, mass, and time explains why even the most advanced propulsion concepts face insurmountable hurdles. Rockets, ion drives, or theoretical antimatter engines all confront the same fundamental limitation. As velocity approaches light speed, energy demands escalate toward infinity. There is no loophole within classical propulsion. Even if we could harness the output of entire stars, the relativistic barrier remains. The universe enforces its speed limit with precision, ensuring that matter cannot outpace light, that causality is preserved, and that the cosmic order remains intact. Yet human imagination refuses to yield. Theoretical constructs like warp drives and wormholes emerge in the creative fringes of physics. A warp drive, in principle, would compress space-time in front of the spacecraft and expand it behind, allowing the craft to traverse vast distances without locally exceeding light speed. Wormholes could create shortcuts through the very fabric of space-time. These ideas exploit the flexibility of space-time itself rather than defying relativity. But they demand exotic forms of energy, negative mass, or conditions that remain purely hypothetical. While tantalizing, these concepts underscore a vital lesson. The laws of physics permit speculation, but they impose absolute constraints on practical reality. Light speed limitations are also reflected in the cosmic scale. Light from distant galaxies takes millions or billions of years to reach us. The observable universe is constrained not by distance alone, but by the finite speed at which information travels. Stars, planets, and cosmic events remain out of reach, not merely because of distance, but because no object carrying mass can accelerate fast enough to overcome the interstellar gulf. Even as we peer deeper into space, we are witnessing events that occurred long ago, yet remain separated from us by an unbreachable speed barrier. Relativity also reshapes our understanding of simultaneity and causality. Events that appear simultaneous to one observer may occur in a different order for another moving at near light speed. Cause and effect remain locally consistent, but the perception of temporal order becomes relative. Attempting to travel near light speed does not merely push the limits of energy. It warps the very structure of space-time, making our intuitive understanding of events unreliable. The universe enforces its rules not only through energy, but through the geometry of space and time itself. Even subatomic particles reveal the consequences of these limits. Electrons, protons, and other particles and accelerators reach velocities unimaginably close to light speed, yet they never touch the ultimate barrier. Each tiny increment of speed requires more energy, and time dilation becomes measurable. The particles themselves demonstrate the universe's insistence on consistency. The cosmic speed limit applies universally, from the smallest scales to the largest. The laws of physics are unwavering, absolute, and remarkably elegant in their constraints. Ultimately, the cosmic speed limit is more than a technical boundary. It is a profound statement about the nature of reality. It defines the structure of space-time, links energy and mass, governs the flow of time, and constrains the reach of matter and information. It is both a boundary and a guide, shaping the universe in every attempt to explore it. The impossibility of reaching light speed is not a flaw or limitation imposed on us. It is a window into the deep coherence of nature, a reflection of the delicate balance between possibility and constraint that underlies existence. Now, we will explore speculative physics, exotic propulsion concepts, and the theoretical loopholes that physicists have imagined. We'll examine how warp drives, wormholes, and space-time manipulation could, in principle, allow journeys seemingly faster than light, and why even these remarkable ideas face profound limitations. As we move from the concrete consequences of relativity to the imaginative fringes of physics, we enter a realm where the impossible flirts with the plausible. While no object with mass can locally exceed the speed of light, physicists have explored ways that might allow apparent faster-than-light travel by bending or manipulating the fabric of space-time itself. These ideas do not violate Einstein's equations. Rather, they exploit the flexibility of space-time and energy distributions in ways that challenge our classical intuition. Here, theory meets imagination, and the cosmic speed limit becomes not a wall, but a lens through which we examine the boundaries of possibility. One of the most famous theoretical constructs is the warp drive, sometimes called the Alcubierre drive after the physicist who first formulated it mathematically. The idea is deceptively simple in concept. Rather than moving a spacecraft through space in conventional sense, one could compress space-time in front of the ship and expand it behind. The ship itself remains stationary within a bubble of space-time, avoiding local motion faster than light, while the space around it effectively transports it at superluminal speeds. From the outside, the ship appears to traverse enormous distances in moments. In principle, this could allow journeys to distant stars without violating the fundamental limit that nothing can locally exceed the speed of light. Yet the practical challenges are staggering. Creating a warp bubble requires exotic matter, material with negative energy density, something not found in everyday matter and only partially understood in theoretical physics. The energy required for a practical warp drive, even with optimistic assumptions, dwarfs the output of entire planets or stars. The universe allows the mathematics, but not necessarily the engineering. It is a tantalizing vision, a glimpse into a cosmos where light-speed travel is conceptually possible, yet technologically unattainable with anything remotely within human reach. Similarly, wormholes, hypothetical tunnels connecting distant points in space-time, offer another avenue for apparent faster-than-light travel. A spacecraft entering a wormhole could instantaneously appear light years away, bypassing the space in between. Wormholes emerge naturally from certain solutions to Einstein's equations, particularly those involving exotic configurations of mass and energy. However, like warp drives, they require conditions far beyond our current capabilities. Maintaining a stable wormhole would demand negative energy, extreme pressures, and control over space-time that humanity cannot yet approach. They remain, for now, fascinating thought experiments that illustrate the malleability of the cosmos while highlighting the ultimate enforcement of relativistic limits. Even beyond warp drives and wormholes, time itself becomes a key player in relativistic travel. As a spacecraft approaches light speed, time dilation stretches the traveler's experience. Journeys of decades could correspond to centuries or millennia outside the vessel. In principle, near-light speed travel could allow humans to explore distant regions of the universe from a subjective perspective, though the rest of humanity would age far faster. This opens profound philosophical questions. Is traveling near light speed equivalent to moving into the future, and what are the ethical and social implications of such temporal displacement? Relativity transforms not just distance but the flow of life, linking the speed limit to the very passage of time. On the microscopic level, quantum physics offers additional perspectives. While relativity imposes strict limits on matter, certain quantum phenomena, like tunneling or entanglement, hint at ways information or influence might traverse space in ways that feel faster than light. Quantum tunneling allows particles to cross energy barriers instantaneously under specific conditions, though it does not permit the transmission of usable matter or information faster than light. Entanglement links particles across vast distances, producing correlations that are instantaneous, yet cannot be used to send messages in violation of causality. These effects illuminate the subtle ways the universe balances possibility and limitation, allowing extraordinary phenomena while preserving fundamental laws. The key insight from all these speculative scenarios is that the universe is flexible yet absolute. Relativity forbids local speeds exceeding light, but space-time itself can warp, stretch, and bend. Quantum effects can seem to transcend distance and time, yet still respect causality. Exotic solutions exist mathematically, but translating them into physical reality faces constraints so severe that they remain beyond practical reach. The speed of light is the ultimate arbiter, and every proposed loophole operates within the boundaries it enforces. It is not a mere barrier. It is a structural feature of the cosmos, a lens through which all motion, energy, and information must operate. Even futuristic propulsion concepts, antimatter engines, photon sails, and nuclear pulse drives must contend with relativistic limits. As velocities increase toward the speed of light, energy requirements climb exponentially. Collisions with interstellar particles become catastrophic at near-light speeds. Radiation intensifies, and shielding becomes a monumental challenge. The dream of reaching distant stars within a human lifetime collides with the immutable laws of physics. Here, the universe is not hostile or arbitrary. It is consistent, precise, and beautiful in its logic. It enforces constraints, yet offers pathways for imagination to explore the boundaries. The impossibility of surpassing light speed also informs our understanding of the cosmos itself. The finite speed of light sets the observable horizon, limiting how far we can see and interact. Galaxies beyond a certain distance are forever unreachable because even light, moving at the ultimate speed, has not yet arrived. Information cannot travel faster than this cosmic speed limit, meaning the universe is compartmentalized in both space and time. Every signal, every photon, and every particle respects its boundary, shaping the structure of reality on the grandest scales. Yet, within these limits, life, exploration, and understanding flourish. The impossibility of light-speed travel does not prevent curiosity, creativity, or discovery. Instead, it imposes a framework within which ingenuity can thrive. It challenges us to rethink our approaches to space travel, energy, and technology, inspiring concepts like relativistic ships, suspended animation, and megastructures designed to circumvent the limitations indirectly. Physics sets boundaries, but imagination finds ways to navigate them, revealing a universe rich with possibilities even within strict constraints. As we consider these extremes, a subtle lesson emerges. Limits define reality, but they also define opportunity. The speed of light is not a wall to be broken, but a horizon to understand. Every restriction, every unbreakable rule, reveals something profound about the structure of existence. Matter, energy, space-time, and information are all governed by principles that are consistent, precise, and unforgiving. By studying them, we not only learn why light speed is unattainable, but also glimpse the profound elegance and coherence of the cosmos itself. Now, we will reflect on the philosophical and practical implications of these cosmic constraints. We will explore how understanding the speed limit illuminates the nature of the universe, the possibilities for future exploration, and the delicate balance between human ambition and the immutable laws of physics. As we arrive at the conclusion of our exploration, the cosmic speed limit reveals itself as more than a technical constraint. It is a profound statement about the nature of reality itself. Light speed is not an arbitrary number. It is a boundary woven into the fabric of space-time, a constant that dictates how energy, matter, and information move through the cosmos. Every electron, every photon, every spacecraft is bound by this limit, and yet within this constraint lies the remarkable structure of the universe, the stage upon which all events unfold. Understanding this limit illuminates not only the physics of motion, but also the principles that govern existence itself. The absolute impossibility of accelerating matter to light speed has consequences that ripple across scales. On a human level, it defines the practical boundaries of interstellar exploration. Even our most advanced propulsion concepts, nuclear rockets, antimatter engines, or laser sails, face exponential energy requirements that make reaching light speed unattainable. Each fraction of velocity closer to see demands increasingly more energy, forcing us to confront the limits of technology, resources, and human endurance. The universe enforces this law with unwavering precision. No clever engineering or futuristic material can bypass it. On a cosmic scale, the speed of light shapes the very structure of reality. It determines the observable universe, sets a horizon beyond which galaxies remain forever unreachable, and preserves causality, ensuring that cause and effect follow consistent order. The finite speed of information underpins every interaction, from the light that illuminates distant worlds to the gravitational waves rippling across space-time. The universe is not merely a collection of objects, but a network of interactions bound by this universal limit. Light speed is the invisible ruler by which all cosmic events are measured, a constant that unifies the behavior of matter and energy across vast distances. Yet the impossibility of reaching light speed does not diminish human curiosity. It refines it. The cosmic limit inspires us to explore alternative possibilities, from near light speed travel, using relativistic physics, to speculative concepts like warp drives and wormholes. These ideas, while currently beyond reach, are intellectually thrilling. They demonstrate that the universe is both constrained and imaginative, a realm where strict rules coexist with extraordinary possibilities. By understanding the laws that govern motion, we gain the insight to innovate within their framework, shaping exploration in ways that respect reality while pushing its boundaries. Time dilation and length contraction, consequences of relativistic travel, further deepen our appreciation of the universe's subtlety. Near light speed journeys warp time and space, creating experiences radically different from those at rest. Travelers may age months while decades pass outside their vessel, while distances shrink along their trajectory. These effects are not theoretical abstractions. They have been confirmed in particle accelerators and satellite experiments. They remind us that approaching the speed limit does not simply change velocity, it alters perception, stretches reality, and connects motion, time, and space in an intricate dance. Even in the realm of speculative physics, the speed limit maintains its authority. Warp drives, while mathematically conceivable, require exotic forms of energy and negative mass that remain beyond our technological horizon. Wormholes, similarly, exist only in theoretical models, requiring precise conditions that are unlikely to occur naturally. Quantum effects like tunneling and entanglement hint at phenomena that seem faster than light, yet they respect causality and cannot be used to transmit matter or information in violation of relativity. Across every scale and every scenario, the laws governing light speed are enforced, revealing a universe both rigorous and wondrous. Philosophically, the cosmic speed limit offers profound insight into our place in the universe. It is a reminder that reality is structured, constrained, and intelligible. Limits are not mere barriers. They are guides that define the shape of possibility. The laws of physics impose boundaries, but within those boundaries, creativity, curiosity, and understanding flourish. Humanity may never traverse the stars at light speed, yet the exploration of physics, mathematics, and imagination allows us to glimpse the vastness of the cosmos in ways that transcend physical travel. Knowledge becomes a vessel that moves us faster than any ship ever could. The impossibility of surpassing light speed also deepens our sense of wonder. It emphasizes the grandeur of the cosmos, the immensity of distances, and the elegance of physical laws. The fact that energy, mass, time, and space interact so consistently to enforce a universal limit speaks to a profound harmony underlying reality. While we cannot break this law, we can study it, respect it, and use it to explore the universe in ways that are both practical and deeply imaginative. The boundary is not a wall, but a lens through which the universe is revealed, highlighting the delicate interplay of matter, energy, and space-time. In understanding why nothing can reach light speed, we also appreciate the extraordinary coherence of physical law. The universe is not chaotic or arbitrary. It is consistent, predictable, and exquisitely balanced. Relativity ties together energy, momentum, mass, and the geometry of space-time. Quantum mechanics adds layers of probability, entanglement, and uncertainty. Together, these frameworks illuminate the rules that govern the cosmos, revealing why light speed is insurmountable and why the laws of physics are simultaneously strict and beautiful. Ultimately, the story of why we can never reach light speed is a story of cosmic perspective. It teaches us humility, inspiring awe at the precision and order of the universe. It teaches us creativity, encouraging us to imagine new methods of exploration within immutable constraints. And it teaches us wonder, showing that even when limits exist, the cosmos offers endless opportunities for discovery, insight, and philosophical reflection. The speed of light is a boundary, yes, but it is also a guide, illuminating profound interplay between possibility and impossibility that defines the universe. In the final analysis, we see that the impossibility of reaching light speed is not a limitation on curiosity. It is a window into the architecture of reality. Every star we observe, every particle we study, every concept we imagine exists within a cosmos constrained by this universal law. Through understanding, imagination, and exploration, we can traverse distances of knowledge far beyond the physical limits imposed by light. The universe remains vast, beautiful, and mysterious, and our awareness of its speed limit only enhances the depth of our engagement with it. The speed of light stands as both boundary and beacon, a reminder of the elegance and consistency of the cosmos. While we cannot accelerate to it, we can approach it in understanding, in imagination, and in exploration. By studying its consequences, we gain insight into energy, mass, time, space, and the structure of the universe itself. The impossibility of surpassing light speed is a truth that terrifies, inspires, and enlightens, an immutable law that reveals the profound beauty of reality and the endless horizons of curiosity that define our place within it.